One of my favorite stories growing up was Flatland. It depicts a society which has developed in the two-dimensional world. The flatness isn't so much a restriction, more than just a different way of life. But what really are dimensions? Well, we could start with a point, that's zero-dimensional, and we could stretch it into a line, making it 1D, or stretch it in a different direction to give us a square, that's 2D. One more time would give us a cube, 3D. These are examples of objects to which we may assign a geometric dimension. And let's summarize these in a table, and note down the formulas we know for their sizes depending on their side lengths. And we can do the same for circles and spheres as well. This time, writing their sizes, how they relate to the radius. Notice how the geometric dimension of each shape matches the exponent used to compute the object's size. And that's no accident. Actually, every shape has a corresponding exponent, and that exponent captures how size changes as we scale the object. But it's harder to see for some shapes more than others. So for instance, let's consider this fractal, which we produce by discarding the middle 1/3 from all its line segments, doing it infinitely often. The resulting set is called the middle thirds Cantor set. But what's its dimension? Is it 1D? Is it 0D? In fact, its appropriate exponent, or fractal dimension, is actually a number between 0 and 1. And we'll return to this later about why. But what about even stranger fractals, like this Menger sponge? It looks pretty 3D, but actually its fractal dimension is slightly less. Typically, we don't think of dimension as a local property. That is, we shouldn't be able to zoom in on just one point in the set and know just from this point how big or small the entire set is. Instead, we're supposed to be able to zoom out, regard the entire set in order to determine its dimension. But what if that's not the whole story? Let's talk about compression. In compression, we're supposed to be able to take a file, such as this one with a million zeros, and come up with some way to store it more efficiently. Now here's one way. Instead of storing all these zeros verbatim, just store some code which could recreate this file whenever necessary. This code is more compact, but importantly, both the compression and the decompression steps need to be algorithmic. Defining what is an algorithm is a bit tricky. Traditionally, you might use a Turing machine, which is some deterministic model or an agent which may read and write some symbols on an infinite tape following some finite set of rules. This one takes an input of zeros and ones and turns all the ones into zeros, halting when it gets to the end of the input. Equivalently, let's just consider an algorithm to be anything you could write in Python or in your favorite Turing-complete programming language. Now, what if we were to try to compress a file containing the results of a fair coin being repeatedly flipped? Well, without any exploitable patterns, we'd expect to never be able to compress this file much better than just storing it verbatim. This file's hard to compress. And if we let C denote the size of a file after performing compression, we see how a file of all zeros has a very small value for C, making it almost perfectly compressible, whereas we wouldn't expect to be able to shrink the size of a file containing fair coin flips very much, making it almost perfectly incompressible. And we call this value the Kolmogorov complexity of the data, and it will always be this non-negative integer representing the smallest size we can compress the data to. And let's deduce something about our function C. If you have a string S you'd like to compress, well, it's easy to see the printS function will produce S. And immediately this tells us that the complexity of S, C of S, is no greater than just however many bits it takes to express S plus some constant for expressing the print statement, which justifies our use of this normalized complexity term, taking the complexity and dividing it by the length of the original data. Every real number, like 1, pi, e, has an infinite binary expansion, which expresses that number as a sequence of zeros and ones. It'll help our discussion of dimension to treat each real number as an infinitely long file of bits, then. It'd be interesting to see how our normalized complexity function behaves as we consider longer and longer prefixes of that infinite binary expansion. So given a real number, we can make a plot of how that normalized complexity behaves as you try to compress more and more of the bits of that number. It looks pretty erratic at first, but if we proceed onward, we might notice that this point's curve seems to converge, in this case around 0.8. We call this limiting value of the normalized complexity to be the effective dimension of that point. And with this definition, now we can state our main theorem. So this is the point to set principle, giving us a way to compute the fractal dimension of a set from effective dimension of the points in that set. The fractal dimension of a set is equal to the maximum effective dimension found across all of its points, whose formula we can write out more explicitly. Modulo some caveats, this tells us that a set's dimension comes from its least compressible points, showing that you really can characterize dimension from just a few points in the set. Now, while the proof of this theorem is quite involved, the basic intuition involves looking at how points are covered at smaller and smaller scales. So let's pick a point of maximal effective dimension in our set. We might continually subdivide space into smaller and smaller squares, identifying in which of these squares does this point lie. So actually, the task of computing the first n bits of a point x is equivalent to computing the square at this precision level which covers x. So if we let d denote the normalized complexity of the first n bits of x, you can convince yourself that it only takes n bits of information to determine which square precision level n over d covers x. And so whenever we scale our big set S, say by a factor of 2, the actual size of the set can't increase by more than a factor of 2 to the d. I hope this helps illustrate why compression is related to fractal dimension. But a theorem is no good without an application, so let's reconsider the middle thirds Cantor set. To start, let's discover one of the set's key properties. We're going to try to notice a difference between points which lie inside the set versus outside it. So we can slide x around, expressing it in ternary, and we move the point inside, then outside, then inside, outside, inside again, outside. The trick is looking at what we've cut out. When we remove the first middle, we eliminated all points whose first ternary digit would have been 1. And in the second stage, we've cut out all those whose second ternary digit would be 1. And for stage 3, the third digit being 1, and so on. In effect, this Cantor set only contains the points without any 1s in their ternary expansions. And so they'll look like some combination of 0s and 2s in their expansions. Now, in order to store a binary code for a point x from the Cantor set, we could just convert it to binary and store it like this. But a much more efficient way would be to take the ternary expansion of x and convert all the 2s into 1s. This code's definitely going to be shorter because the ternary expansion of x gives us a more precise approximation to x per new digit. Now, the exact factor by which we can compress the bits of x in this way is simply going to be the ratio of how many bits it takes to describe one of the possible codes for x to precision 3 to the minus n versus how many bits it usually takes to express a real number to the same level of precision. Finding the number of bits in either case is just like taking a log, and so we can simplify and find our compression factor to be log 2 over log 3. This is enough to tell us that no element of the Cantor set can have an effective dimension larger than this compression factor. But since any combination of 0s and 2s is possible for a point in the Cantor set, there's got to be some points in this set that have maximal incompressibility, meaning they're going to have an effective dimension equal to our compression factor. And so, by the point to set principle, now we know the fractal dimension of the Cantor set is actually equal to our factor of log 2 over log 3, settling this example. A similar argument could have helped us compute the fractal dimension of even stranger fractals like the 𝘦𝘧𝘧𝘦𝘯𝘴𝘪𝘰. And so if nothing else, I hope you take away from this video that the dimension of a shape really can be related back to the incompressibilities of its points. And this gives mathematicians a whole new computational way to approach geometry. Well, thank you so much for watching. This was a really fun video to make, and I hope to see you next time.